Hey everyone, welcome to part 4 of the sensor fusion tutorial. And now we're going to start to describe the detection pipeline. So in this pipeline we're actually going to use YOLO v5. I've already cloned it, installed the requirements, imported the model, and I've just changed the confidence and IOU thresholds a little bit, but the default parameters seem to work fine. I'm just a little nitpicky with it. So our detection pipeline is going to have 5 main steps. First is going to be to detect objects in the camera image. We're going to use YOLO for that. Second, we're going to project the LiDAR point cloud to camera space using the transformations that we've derived. And this is going to be our fusion step that allows us to fuse the LiDAR point cloud data with our image data that comes from the camera. And now we're going to associate object centers with the projected LiDAR points. This is going to be implemented with a simple function. And then we just have 2 transformations. So the first transformation is going to be particularly useful. We're going to transform image space coordinates to IMU space coordinates. So this is going to allow us to work with the ego vehicle's own navigation data, such as lat long altitude. We're going to have different velocities relative to the IMU. So we're going to want to work in IMU space for that. And then finally, this is more of an optional step, we can transform IMU coordinates into lat long and out. So we're going to actually be able to see where these objects detected are in the real world, and we could actually plot them on a map, and we'll do that later. So I'm going to talk about this one function right here called get detection coordinates. This takes our image and a binary path. This is our LiDAR point cloud path, and it's a binary file. So first thing we do in this one is we get our detections from the model. And this is our YOLO 5 model. And we're going to want to draw the boxes on the image just to see what the model detects. And then this right here, with our detections object, we could actually dot XY, XY, and this gives us our bounding box locations along with their probability and class. And we're going to make sure this goes on the CPU since I'm using a GPU runtime. And this function right here, this is a kind of a function that takes care of everything. It's called, project velobin to UVZ. This takes our binary path, our transformation matrix from LiDAR to camera to UVZ space, our image, and this boolean called remove plane. So let's go find this function in our utils script. So right here, the first thing we're going to do is we're going to read in the binary, and we're going to get our x, y, z, w coordinates. So this is homogeneous coordinates right here. So this function, we use numpy to read the binary. We get our XYZ points from our scan data. We delete negative LiDAR points because there is kind of some wonkiness to the LiDAR. And if we keep the negative points, we're going to get weird results. So we get rid of those. And this right here, this remove plane, we actually use unsupervised learning to remove the ground plane. So this RANSAC it stands for Random Sample Consensus. And basically what it does in 2D space, it tries to find the best line. Now it's going to basically give a bunch of random samples. It's going to randomly place lines in the points and see how close it is to the surrounding points. And right here to the right, we can see a fully converged RANSAC. We can see it's very obvious that these points right here make a line, and RANSAC has found this. And in our 3D LiDAR space, this is actually, for the most part, what we get with the ground plane. The ground plane is a very obvious line. The LiDAR is very accurate, and RANSAC almost always removes the ground plane, and it does it pretty well. And we'll see this coming up. So that's what this does. We basically, in this code right here, we delete the ground plane, and then we convert it to homogeneous coordinates. So that's what this W means. So in this next function right here, we have XYZW to camera. All this does is this converts homogeneous LiDAR space into camera space, and we have our camera rotation matrix right here. Let's go look at this one right here. So we convert it to left camera coordinates, and once again, if there's any negative camera points, we're going to delete those. And now we're going to convert to UVZ coordinates and normalize. So that's what we're doing right here. We're dividing the UVZ by the Z component right here. And so now we're going to get UVZ instead of UV tilde. And now we're going to do something called remove outlier. So basically, once we convert to LiDAR to camera space, we're likely going to get some points that are outside of the camera's frame, and we're just going to remove those to make things easier for us. So that's what this code does right here. So, and that's all of this. Once we remove the outliers, we get the LiDAR LiDAR points projected to camera UVZ space, and that's what this is right here. So back in here, once we have our LiDAR points, now we have our object detections and we have our LiDAR points. So our object detections are stored in this B-boxes array, and we're going to pass this to get UVZ center. So this is the function that does the association that gets the camera, get the LiDAR projected points that are associated to the object center. So let's go through this one up here. So first thing we're gonna do, we're gonna unpack the LiDAR coordinates, which just makes things easier, and we're gonna actually produce a new output. We're gonna store in our bounding boxes array the LiDAR projected UVZ coordinates that correspond to the centers of the detected object. So we're going to iterate through each of the detections and bounding boxes. We're going to take the center of the detected object. We're going to take the this is the top left point, and this is the top right point, and we're going to make sure this is not a torch. We're going to convert it back to NumPy, and we're going to take the object center, and just keep in mind this is still going to be a float. We're not putting that to an integer yet, and we're also going to take the delta, so we have every single LiDAR VU point right here, and now we're going to make sure we take the delta of that. So remember, in this case, V is getting subtracted by X and U is getting subtracted by Y. So now we're going to get the minimum location, and this minimum location is going to allow us to get this depth value right here to get from the Z frame. And now we're going to just get the UVZ location, we're going to add it to bounding boxes, and if we want to draw it, we're going to convert the object centers back to integers, and then we're going to use OpenCV's put text function. We have our image, our text, the location, so it's going to draw it at the top left of the text is going to be this object center right here that we're passing to it. We have the font, our font scale, color, thickness, and line style, and then we return the newly formed bounding boxes out. So this is kind of the main portion of the detection pipeline. I'm going to scroll down and show you how this is implemented. So we get our data. We're going to need image data, our LiDAR data, our GPS data, and then we're going to run this thing in a one-liner. We're going to get our bounding boxes with our object image space locations with depth, and we're also going to get all the LiDAR points that we're going to make use of later. So now we're going to get transformed coordinates. We're going to transform these to the IMU. So we're basically going to extract these from here just to make things look nicer, and then we're going to run this through transform UVZ, which is imported from our utils function. So we have our transformation matrix that we've already derived that takes us from our left camera to the IMU. So let's go see what this function does. So right here, we convert this UVZ to homogeneous. We can see right here we're undoing the normalization, where we're multiplying by Z to undo the normalization that we've done, and then we're adding ones. So this basically gives us a UVZW array. And now that we've converted the homogeneous, we could actually perform the transformation, and then we could just neglect this W right here and just get these XYZ coordinates, and that'll give us the XYZ from UVZ. And notice how this matrix right here, we could actually convert this to Velodyne. We convert it to another camera as long as we have the correct transformation matrix right here. So that having the correct transformation matrix is key to this, and that's why we spent so much time deriving it earlier. So in this next function right here, just for fun, if we want to, we can convert to lat long out. So I have a function called IMU to geodetic. So it takes in our XYZ, our lat long out, and our heading of the vehicle. So we extract these from the GPS data that we've read in above, and I'll go through getOxt. It's a pretty simple function. It just allows us to read in our GPS data from our GPS text files. Oxt is the brand of GPS, so that's all it does right here. So let's go through IMU to geodetic, and I'll show you how to go from XYZ coordinates to lat long and out. So we're going to use a library called PyMap3D, and we're going to import that right here. So the first thing we're going to convert it is to slant range, azimuth, and elevation. Three simple equations. It's actually basic geometry. You can see right here. This might remind you of the Pythagorean theorem. And then we're going to use a built-in function from this library called PyMap 3D. So this is AER, it's a geodetic. It takes as, L, range, and lat, long, and altitude. And if you see above here, we do need to compensate for the azimuth and get the correct heading. So, and then also we needed to add this 90 right here to the elevation to get proper elevation that this function wants us to put in. And finally, we convert it to a NumPy array, and we get the lat, long, and altitude. So real quick, we could test this pipeline. We're going to run it. I have a function called draw velo on image just because I want to project the LiDAR data to the image. So we can go through this here. So all it does is unpacks the UVZ coordinates, iterates through them, and puts a circle on the image. Now, we could do a scatter plot, but doing it in this manner will allow us to save the image much more efficiently than trying to save a scatter plot. So we're going to plot these right now. So right now what I'm doing is I'm combining the left image that we had and the velo image. So we're basically drawing the LiDAR point cloud onto a blank canvas right here. So right here we can see that we've almost completely removed the ground plane. You can see there's a little bit of stuff right here on the sides, a little bit here, and then some stuff up front. But for the most part, the ground plane is removed, and we can clearly see these clusters right here that correspond to cars, and we can just look above up here. And we can see depth information. Now, depth is going to be in meters right here. We can see that's about 10 meters away. That's about 10. It's 9. So this is actually doesn't account for XYZ. It's just pure Z depth. So this looks about right. And in the next video, we're going to see how to sanity check this, and we're going to actually use what we know about the ego vehicle to do that. So I'll see y'all then. Take care.